Okay, hello everyone. Good evening, good afternoon, good morning perhaps. Welcome to the latest seminar in the seminar series of the International Network on Quantum Annealing. I'm very pleased to say that we have a speaker from the group of Misha Lukin in Harvard today, who's, although many of us on this audience are used to thinking about superconducting qubits, there's been some really impressive work also in neutral atom systems. And it's my great pleasure to introduce Maddie Cain from Harvard, who will tell us about that. Over to you, Maddie. Thank you very much.
Thank you. Hi, everyone. I hope you're having a good day. As Paul said, my name is Maddie, and I'm a grad student at Harvard in Misha Lukin's group. And today I'll be telling you about our work that's looking at the quantum optimization of the maximum independent set problem using a Rydberg atom array quantum computer. So our work is motivated by the prospect of demonstrating quantum speedup on near-term devices where we can control, say, hundreds or maybe even thousands of qubits, but we don't yet have error correction at scale. And we asked ourselves if there's a problem that we can demonstrate quantum speedup on that is a useful problem in the near term. Where here I'm defining quantum speedup as just the runtime scaling more favorably with the problem hardness for a quantum algorithm as compared to its classical analog. And of course, there are many known quantum algorithms that have speedup, but today I'd like to focus on those which can be implemented on these near-term devices. In particular, I'll be focusing on combinatorial optimization. And this is a broad set of problems with the goal of optimizing a cost function subject to constraints. These problems are known to be NP complete and intractable to solve in the worst case for both classical and quantum algorithms, but they're general enough such that if we could solve one NP complete problem, we could solve all NP complete problems. Today, I'll be focusing on a pretty popular NP complete problem called the maximum independent set. The goal here is that we're given a graph, a set of vertices or nodes connected by edges, and we'd like to maximize the size of a subset of those vertices subject to the independent set constraint, which states that no two vertices in our subset are connected by an edge. So here I show the maximum independent set of our graph in red, and this is the independent set that we would like to find, or at least get a good approximation of perhaps a very large independent set. Today I'll be focusing on the MIS problem on unit disk graphs, which is a class of graphs where we have an edge between two nodes if and only if they're within a unit radius. And MIS on this class of graphs is known to be NP complete, but it has the additional benefit that it's really naturally implemented in our Rydberg atom array hardware. There's a very hardware efficient encoding, which I will now describe. So as a brief outline, first I'll talk about how we encode quantum algorithms for MIS on the Rydberg atom array platform. And then I'll get into our work where we benchmarked our quantum algorithms against classical simulated annealing in two regimes of finding approximate solutions to MIS as well as finding exact solutions. So first, we encode the MIS problem on the Rydberg atom array platform by taking several hundred rubidium atoms, each of which can be thought of as a qubit, and we arrange them deterministically in 2 dimensions. So here I show an actual snapshot of the atoms in a configuration in 2D that we've chosen. And our encoding will be such that each qubit will represent a node in the graph we want to find the MIS of. In particular, each qubit is a 2-level system with a hyperfine electronic ground state, which represents that atom or node is out of the independent set, and then a highly excited Rydberg state that represents that atom is in the independent set. And then we can do single qubit rotations on this manifold with some Rabi frequency omega and detuning delta, which just give us sigma x, sigma z type terms in the Hamiltonian. Next, Ryd atoms can interact with nearby atoms via what's called the Rydberg blockade mechanism. And this is a spatially local interaction that prevents simultaneous excitation in the Rydberg state of atoms within some radius, which we'll call the blockade radius. And we'll design the problem such that our blockade radius will set the connectivity of our graph. In particular, we'll say two atoms or nodes are connected by an edge if and only if they're within the blockade radius. The reason that we do this is that the Rydberg interaction then really naturally encodes the independent set constraint on unit disk graphs, where the unit radius is just the blockade radius, and the strong energetic penalty on two atoms nearby occupying the Rydberg state is just enforcing the fact that two atoms connected by an edge can't simultaneously be in the independent set. Putting everything together, our Hamiltonian is a quantum driver type term with a phase and also some strength, omega, as well as a cost function type term. And this cost function Hamiltonian includes two terms. The first is our detuning, which when it's positive favors many nodes being in the independent set, and it's low energy manifold, and the Rydberg interaction will penalize independent set violations. So putting everything together, we notice that the ground state of this cost function actually is the MIS, and our goal will be to implement quantum algorithms to find this ground state. So I'll discuss how we implement the quantum adiabatic algorithm, which we'll focus on mostly today, and I'll briefly mention also our implementation of QAOA. So for the adiabatic algorithm, what we do is we initialize the atoms in their atomic ground state, which when the detuning is negative also corresponds to the many-body ground state. Then we'll evolve our system adiabatically, turning on and off our sigma x type term. And while we sweep the detuning from negative to positive, such that the final ground state, if we've evolved slowly enough, will encode the MIS of the graph. We then optimize the adiabatic evolution by essentially having a classical optimizer parameterize our adiabatic suite and find the optimal detuning ramp that we can do for our adiabatic algorithm. And similarly, we do have a similar parameterization for QAOA where we're optimizing over the laser phase. To then optimize our algorithm, for a given set of parameters, we'll repeat the parameterized evolution many times to compute some figure of merit, say the independent set size. And then we'll use closed loop quantum classical optimization to optimize these parameters over the figure of merit. So we can then do a performance comparison for our implementation of QAOA as well as the adiabatic algorithm. And here the figure of merit we look at is the approximation ratio, which is just the mean independent set size divided by the size of the MIS. So when R is equal to 1, you found the perfect solution. For QAOA, so here I'm plotting 1 minus R as a function of depth. And what we see is that the performance gets better and better up to about depth 4, with 1 minus R correspondingly equal to 0.25. On the other hand, for the adiabatic algorithm, if we plot 1 minus R versus depth, which here is just the evolution time divided by the time to flip a spin, we see, particularly for the optimized detuning sweep, that 1 minus R reaches much better values of about 0.09. And we attribute this better performance of the adiabatic algorithm due to a mixture of both experimental imperfections as well as the difficulty of optimizing the QAOA with our finite shot noise, basically. So now that I've kind of introduced the adiabatic algorithm, our goal was to benchmark the performance of that adiabatic algorithm against classical simulated annealing and finding approximate and exact solutions. So to benchmark quantum performance, we studied the adiabatic algorithm on about 100 instances with up to 289 nodes. So here I show 4 different instances and I plot 1 minus approximation ratio versus the algorithm depth. On all 4 instances, we see that performance is getting better and better up to a certain point, which kind of sets the coherence time of our device. And what we see is that even though we have 4 different instances, and these actually correspond to about the same system size, there's a lot of variation in performance. And we really wanted to understand what was controlling the performance of the adiabatic algorithm. So we split our analysis into 2 regimes, which we study separately. And the first is kind of the high energy regime, which you can think of as corresponding to how does our algorithm approximate solutions to the MIS problem. In the low energy regime, We're looking at how well is our algorithm doing at finding near exact solutions. So we start with studying approximate solutions. So first, what we do is we look at fixed system size, and we look at several different instances, which I show here. So here are 4 different instances of different colors. What we see is that even though all these instances have the same system size, which normally people think of as a proxy for how hard the algorithm is going to have to do at finding the performance, there's actually a huge variation within system size. And furthermore, if we look at many different system sizes and we plot performance at some fixed depth, we see again that there's a huge variation even within a single system size of ranges of hardness for the quantum algorithm. This motivated us to try and understand what really is controlling the performance of the quantum algorithm in this regime of finding approximate solutions. So we had some intuition that maybe the degeneracy of the graph, or the degeneracy of the MIS, which is the number of MIS solutions, might have something to do with the hardness for the quantum algorithm. The rough intuition being that, okay, if you have more solutions to the problem, it might be easier to find or approximate those solutions. And indeed, when we plot 1 minus approximation ratio versus the graph solution degeneracy, here is for a single system size, we find that the 2 quantities are strongly correlated, indicating that our intuition at least was somewhat correct. Next, we wanted to understand how we could understand this phenomenon of degeneracy controlling performance at many different system sizes, because we know that generically the degeneracy seemed to grow exponentially with the system size. So we needed some way to normalize this quantity for different system sizes. And we ended up finding that at fixed depth, the performance seems to be controlled by the degeneracy density. Here, the log of the degeneracy, since it's exponential, divided by the system size, which you can kind of think is like the intensive analog for degeneracy. And so here I show 1 minus R versus the degeneracy density, and we see a strong collapse of performance for all different system sizes, indicating that this is at least strongly controlling the hardness for finding approximate solutions. And we have hypothesized what might be going on here is that something similar to Kibbles-Reck type physics, where our adiabatic algorithm, at least at shorter evolution depths, is solving local correlated regions. And in this Kibbles-Reck mechanism, you can in general have domains along the boundaries of these correlated regions that cause imperfect approximation ratio. And what we show is that in the limit of a small amount of disorder, you introduce degeneracy to your solution space, but this degeneracy can make it such that when you put 2 domains together, the domain wall may accidentally not cause a imperfection in your system, just due to the fact that you have more freedom in how you place these domains together. So that was a kind of phenomenological explanation for what was going on here. Next, we wanted to benchmark our algorithm against classical simulated annealing. So simulated annealing, for those that may not know, is a really, I think, fundamental classical algorithm that simulates classically cooling to the ground state of the cost Hamiltonian by stochastically flipping spins. And often people think of it as kind of some classical analog to the quantum adiabatic algorithm, because you're trying to essentially classically cool instead of doing a 0 temperature adiabatic ramp. And the way that simulated annealing works is basically the simulated annealing state is a spin configuration, and you'll propose to modify the spin configuration by flipping some local cluster of spins. And then you will accept this proposal with a probability that depends on the inverse temperature beta, as well as the change in energy under that update. After many updates, SA is guaranteed to prepare a thermal Gibbs state at the temperature that you're working at. And then what we do is, for our particular SA implementation, we can optimize the SA so that we're trying to compare our quantum algorithm against the best SA algorithm possible. And we optimize several things, including how we change the temperature as a function of algorithm depth. We do collective updates and stuff like that. Next, so we want to now compare our performance of our quantum algorithm against SA. And so here I'm again showing 1 minus approximation ratio versus depth. And now SA is plotted on the same axes. SA is the solid lines. And the depth for both algorithms is basically the total evolution time divided by the number of spin flips effectively. And what we find is that at short depths, or finding approximate solutions, we actually have comparable quantum and SA performance, both algorithms seeming to depend on the degeneracy density. And this kind of, I guess, is consistent with the idea that Kibble-Zurek type physics can happen in both quantum and also thermal systems. On the other hand, we see that the story seems to change at finding exact solutions, which I'll talk about next. And in particular, what we see is for some instances, such as the purple and gold instance, the simulated annealing algorithm seems to have a hard time in finding the solution up to very high depths. And the approximation ratio plateaus at a value that corresponds to SA being trapped in local minima of the MIS size -1. In effect, SA is trapped in local minima and it can't find the solution. And so our figure of merit now that we'll be looking at is the MIS probability of finding the exact MIS instead of an MIS -1 state. So we can understand why SA is having trouble in finding the MIS on these hard instances by visualizing its dynamics on a configuration graph. So for a configuration graph, the nodes actually represent individual independent sets, either an MIS -1 state in blue or an MIS state in red. And the SA will walk on the edges of this graph, which just represent a single SA update. And the key thing to realize here is that among the MIS -1 states, they all have the same energy. So under the SA update rule, the dynamics will just be a random walk among these states with the same energy, kind of analogous to the phenomenon of like black box searching for an MIS state. It turns out that we can get rigorous limits to the SA performance based on this intuition. So we define the SA hardness parameter as being large when the number of MIS -1 states is large. Here, this is the degeneracy of MIS -1 states. But the problem should become easier for SA if the number of MIS states is larger. So when this hardness parameter is large, SA will have a harder time of finding a solution intuitively. Indeed, we can actually match this intuition with an analytic lower bound on the SA runtime, as the SA runtime being lower bounded by some quantity that's linear in this hardness parameter. In addition, we can show numerically that the hardness parameter appears to grow exponentially in the square root of the system size in the worst case, indicating that SA should also have exponential runtime on these hardest instances for SA. What this means is that if I look on the right, this is a configuration graph of a 39 vertex MIS instance. But if I increase the system size slightly, the configuration graph goes from looking like this to looking something like this, where we will have very, very long time to actually find these MIS states. So next, what we want to do is we want to select the top 2% hardest instances maximizing this SA hardness parameter and compare them against the quantum algorithm. So here I plot the top 2% hardest instances up to 80 vertices against the SA hardness parameter. And I find that the SA runtime is linear in the hardness parameter. This matches the theoretically best possible runtime for SA as given by our analytic runtime lower bound. Then we can run the same instances using the quantum algorithm and compare their analogous runtime. What we find if we look at two example instances is that the quantum performance seems to vary a lot on instances with similar SA hardness. So here I show, again, the gold and the purple instance for SA and quantum. And for the SA hardness, they end up having around the exact same hardness parameter. And I'm plotting here the normalized Hamming distance to the MIS versus the depth. So SA is stuck at large Hamming distances from the MIS, whereas for the quantum algorithm, these dotted points, the gold instance, the quantum algorithm approaches solutions that are very, very close to the MIS at very, very short depths, indicating that it's doing much better than SA. But the purple instance seems to have more similar performance to SA. So we see a lot of performance variation for the quantum algorithm, even on instances that have the same SA hardness. Putting this into a broader scale, we run all the exact same instances that we identified as hard for SA. And we can see that if we plot the analogous quantum runtime versus the SA hardness parameter, there's a huge amount of scatter in the data, which indicates that quantum hardness is not going to be determined by the same thing that's determining SA hardness. If we fit the performance of runtime versus hardness parameter, we see that the QAA runtime on average is very similar to the SA runtime, with a slightly sublinear scaling. However, this motivated us to understand, okay, which instances are hard for the quantum algorithm and why, and also which instances, why do we see that the quantum algorithm does so much better on many instances as well. So to understand what's controlling quantum performance, we return to what we know about the adiabatic algorithm, which is that the transition rate out of the many-body ground state is set by the minimum energy gap during our evolution. In particular, here I plot the energy gap versus the detuning of a, I believe, 51 vertex instance. And we see a minimum gap closing generically on these instances that should set how long we need to actually evolve for to find, to remain adiabatic in our evolution. So the question we wanted to ask was, are we really experiencing gap-limited physics in our system, which does have some finite amount of noise, and are we really in the regime where the minimum gap actually matters for our evolution? So what we do is we use our optimizer to slow down at the evolution at different values of the detuning. The idea being that if we slow down at a detuning that corresponds to the minimum energy gap, we should see increased probability of the MIS, which is kind of our analog for saying what is the ground state probability at the end of the evolution. And what we find is indeed for this same instance on the bottom and the top plots, if we slow down at a detuning of around 8 megahertz, which corresponds to where our minimum gap happens, we see a hugely increased probability of the MIS, indicating that we are indeed sensitive to this many-body adiabatic gap. We can see this on a larger scale if we look at the same instances as before and plot MIS probability versus the minimum gap. And we can fit this data onto a Landau-Zenner type functional form that has a pretty strong correlation between these two quantities, which I think confirms that we are, to a certain amount, experiencing gap-limited physics. In addition, the fitted dependence of the gap in the Landau-Zenner functional form, for those who may be familiar with this, is linear, indicating that our optimization is such that the evolution time needed is roughly 1 over the gap, which is kind of the best possible scaling that you can have for an optimized adiabatic algorithm. However, what we notice is that for a few of these instances, the minimum gap that we compute here, we're computing it with DMRG, is so small that we can't possibly resolve it during the coherence time of our device. So during our coherence time, we simply cannot resolve this gap as given by the time energy uncertainty principle, and we can't even hope to optimize the algorithm in this case because we really are not having gap limited physics. And what we find is that these are the instances where we do see really poor performance of our device. And so if we then focus on the instances where we can optimize and do have long enough evolution times, and we look at these instances as a function of SA hardness parameter, we find an improved scaling of HP to the 0.63 is deciding our runtime, which, as a reminder, is better than the best possible classical runtime for SA. So in effect, on these instances where we can evolve long enough, we do see a superlinear speedup in the runtime in terms of the hardness parameter. And really this this optimization is really necessary to get a speed up on these particular instances. So in summary, what we aimed to do during this work was really characterize SA and quantum performance and understand if there was any possibility for quantum speedup. In finding approximate solutions, we saw that the SA and quantum approximation ratio was both controlled by the degeneracy density and that they actually had similar performance. Whereas in finding exact solutions, SA was controlled by this hardness parameter and the quantum performance was controlled by the gap. And these two things weren't necessarily very well correlated, which allowed us to see a speed up on certain instances compared to SA. I think that this opens up two interesting outlook questions that I'll just mention briefly. First of all, we wanted to ask what controls the quantum gap, if not this SA hardness parameter. Because if there are different things affecting quantum and SA hardness, then it opens up the possibility of getting a quantum speedup on instances where the hardness really differs for these two algorithms. And then furthermore, how can this inform designing or predicting which problem instances will have speedup? So on the first direction, I just wanted to mention work that we have been doing as a follow-up to this MIS project to theoretically understand the quantum performance. And hopefully this will be out in the next couple of weeks or so. And in this work, what we do is we analyze the adiabatic gap in terms of the eigenstates involved in the level crossing. And we get conditions for a quantum speedup or slowdown over SA. So we can predict if given an instance, will it have a speed up or a slowdown? And this understanding motivates us to actually modify the adiabatic algorithm. It's still a sign-free problem. It doesn't have a sign problem, but we modified the Hamiltonian slightly to obtain a quadratic speed up over SA, and as well as we show that it is a speed up over parallel tempering algorithms as well. Next, I think as more of something that we might look at in the future is if we can use the knowledge that we've gained in understanding quantum hardness to design instances that have a super polynomial speedup. In particular, we can think of the adiabatic dynamics as a quantum walk over the spin configuration graph, similarly to SA. And we can ask if there are instances that have configuration graphs that are easier to traverse for quantum versus classical. And people have done this in the Oracle model by designing graphs that are very complicated and not super physical, but nevertheless have a super polynomial quantum speedup over classical algorithms in solving the problem that they define. So it would be interesting to think about if you can use this idea to generate hard instances for SA where we could perhaps have super polynomial speedup rather than just polynomial. So with that, I would like to acknowledge our many collaborators that we had on this project. In particular, the experimentalists who have worked for years building this platform and optimizing it, and of course, like taking all the data and really leading this effort, as well as my PI, Misha Lukin, and the co-PIs Vladan and Marcus Greiner. And in addition, there was a huge team of theorists that worked on this project, including graduate students, several professors at Harvard and MIT that were collaborating, as well as people from Quera Computing that helped especially a lot on the numeric side. So with that, I am done and I'm happy to answer any questions that people may have.
Good. Thank you very much, Maddie. Very nice presentation. A round of applause on behalf of all the audience, I'm sure. And I'll certainly be happy to open it up for questions. So if you have a question, either just speak up or raise your hand. Maybe I'll start with a basic question, which probably reflects my misunderstanding on my part. But I mean, you were speaking about depth, which I associate with gate-based operations.
Yeah.
Whereas I associate quantum annealing with continuous time operations. So what am I not understanding there?
So we needed a way to compare simulated annealing and quantum annealing. So we tried to think of what is an analogous definition of depth for the two. And so for simulated annealing, we're proposing updates and updating our spin configuration, and we'll count each update, or I guess update of the entire system as depth 1. And the idea for the quantum thing, for the quantum algorithm was, well, the analogous definition would be the time it takes to flip or update all spins under the Hamiltonian. And this definition is somewhat arbitrary, but the key important thing is that if you're talking about polynomial speedups, the definition of depth is somewhat arbitrary, because if you redefine depth up to a constant, you should still see a polynomial difference in the scaling.
Okay, let me ask a very basic question then. Are your fields changing continuously in time, or are they changing in discrete time?
They're changing continuously.
Okay, fine.
Yes.
Perhaps I need to go back and read your papers then. Okay, so we have some other hands raised. I see Daniel Goldsmith's hand is raised.
Yeah, thank you very much. Thank you, Paul. Thanks, Maddie. That's a really interesting talk. Really appreciate it.
Thanks.
Yeah, I'm afraid I've got a really basic question, I'm afraid. So sorry if I've been a bit slow. So when you have examples of the quantum annealing and you have various results from quantum computers, were they real quantum computers, real observational results, or were they simulations that you'd carried out?
So real quantum computers. So the experimentalists actually have built this platform, and there are actually other versions of the platform in many other groups. But for us, we're actually using real rubidium atoms that are our qubits, and you can do gates with those atoms. And we actually, I'm going to show you a picture of the atoms. Yeah, so this is actually like a real picture of the atoms that they basically move around and trap and do operations with. And actually a cool new hardware, I guess, advance in this platform is that we now have the ability to move these atoms around in the middle of the computation. So we can actually have arbitrary connectivity by just moving atoms and maintaining coherence when we move the atoms. So we can do a gate, move atoms, do another gate, stuff like that. So it is like a physical platform that we're running. Yeah.
Okay, no, thanks. That's amazing. And so this is a research computer, or is it a computer that's commercially available? Because it seems it's extremely powerful computer with that number of qubits.
So this one is research, but my advisor started up a company with some other professors that is commercializing the platform. And that company is called Quera, Q-U-E-R-A.
Okay, that's great. A name to watch then. Thank you. Thanks.
Yeah.
And just while we're looking at this slide, Maddie, if I may, so maybe this explains my question. So your driver term is clearly time dependent here.
Yes.
But your cost function is not. Is that sort of cost function permanently on, and you just turn the driver off, or?
I should have delta of t. So
okay.
The detuning delta, so the sigma z type term, is time dependent. So is our sigma x / sigma y type term.
And how about the interaction terms?
That is static in this project. The interaction term is basically set by the distance between two atoms. So the interaction dies off as 1 / distance to the power of 6.
But you were just saying that you can move the atoms. Does that suggest you could meaningfully have some time-dependent interaction term, or do you just vary that quasi-statically? Yeah,
exactly. So if you move atoms, you can change the connectivity of your system. And so we're looking at this, applying this in the context of optimization and getting beyond unit disk graphs. By just moving atoms, maybe with some trotterized QAOA or adiabatic evolution. but it's also, we're also thinking about it in the context of quantum error correction, like interfacing different logical qubits together by moving them and doing gates between them.
And maybe my last question, if I may hold the questions here. So which of these terms are, global, and which of these terms are spatially addressable per qubit?
Okay, that's a great question. So right now, everything is global. However, the experimentalists are upgrading right now such that the detuning, the sigma z type term, is going to be local. I think it may already be locally changeable depending on the qubit in INQA, the startup.
Okay, that's enough questions from me. So there's a question in the chat from Elliot Capit, who writes, beautiful talk, I agree. A quick question, when you talk about modifying the adiabatic algorithm to improve performance in future work, is that tuning the global schedule or adding local variations as well? Maybe that's the same question I just asked, because I worry with global schedule tuning, if the gap is decreasing exponentially in hard instances, then you will eventually run into precision requirements that are unachievable, as you need control precision that goes like 1 over the gap minimum for global schedule tuning. I hope I did that question justice.
You did. No, that's a great question. And I completely agree that, I guess for the broader audience, a really interesting open question that's only been, I think, partially answered, though there's been a lot of progress, is how do you optimize the adiabatic algorithm so that your evolution time goes as 1 over the gap? And that problem we have not solved. And we are relying on the fact that for the system size that we look at, the gap is, I guess, large enough to where we can optimize. But I think that that's a really interesting future direction to explore. And yeah, I don't know. Does that answer your question? Was it Elliot?
Elliot says, yes, thanks.
Okay, good. Yeah. So I think interesting future direction. And it's a very good point.
Umberto has a question.
Hi, Maddie.
Hi.
Hi. Thank you. It was a very good talk. So I take it from your last slide that you are publishing results that include comparisons against parallel tempering, as well as simulated annealing. So can you give any intuition over what your findings are for speed up over parallel tempering, if you're comparing against ordinary parallel tempering or the variant with cluster moves, and any intuition as to what these results that you're finding are?
Yes, but what was the variant that you said with what removes?
Cluster moves.
Cluster moves. Okay, yes. So that's a good question. And as I'm wrapping up the paper, it's something that I'm still trying to strengthen. So I guess as a reminder, for SA, we can actually prove that with any SA algorithm, the runtime is lower bounded by the hardness parameter. And the intuition behind that is that if you satisfy detailed balance in your SA update, which is the only thing that we assume, you can't take many states, which are all of the same Gibbs weight, to a small number of states. There's like a counting argument. And the question with parallel tempering is, let's say that I have many copies of this configuration graph, all at different temperatures. And I'm trying to get one of them into the MIS, only one. The idea, the rough intuition, is that if all of my systems are initially in an MIS -1 state, first of all, replica exchange will not help me, because switching to systems in the MIS -1 state, you're not going to get an MIS. Then what we need to do is understand the performance. Okay, then there are other types of update rules that you could have. You could update a single copy on its own. This is analogous to just running SA. Or you could have a collective update between multiple copies. And for this, the key, we don't obtain a lower bound on any update rule, but rather we obtain a lower bound of the performance on update rules that update a constant number of spins in the system size on each replica. And the idea basically is that if you're updating a constant number of spins in some sort of collective cluster update, in order to get to the MIS, you still have to be among these states that are very close to the MIS. And there's very few of those. There's very few of those states compared to the total number of MIS-1 states. So that's how you get a similar bound for cluster updates.
Right.
Hope that was not too detailed, but yeah.
No, it's very insightful. However, I don't think it would be unreasonable to expect that the size of a cluster update could scale with the system size rather than.
I agree.
Right, but I see this is good intuition behind.
Yeah, and before the paper has kind of like just really two things that I want to see if I can strengthen before I put it out, and that is one of them. Could a more complicated collective update that scales with the system size affect things? It's hard mathematically to show, but that's what I'm trying to see right now.
Right. Well, this looks very good regardless, but thank you.
Yeah, of course.
Any further questions for Maddie? I see no further questions, so let's thank Maddie once again for an excellent presentation. Thank you, Maddie. And look forward to seeing you all at the future INQA seminars in the forthcoming weeks. Bye-bye, everyone.
Thank you.
Thanks, Maddie.